Hello friends, welcome to my YouTube channel. Today in this video, I will be teaching you about the Helical Gear Design. So let us start with our video. But before that, if you like what you see, then don't forget to hit the like button and subscribe to my channel for more videos like this. So let us start with our video. For the topic, our question will be: design a helical gear pair used to transmit power from electric motor rated at 30 kW running at 960 rpm to the machine rotating at 250 rpm. The helix angle is 17 degree and the gear is with 20 degree pressure angle, full depth involute profile. So let us start with our question. So before that, we will write what data is given in the question. The first is power, that is 30 kilowatt. After that, N1, that is 960 rpm, that is rotating speed of motor. Then after that, N2 is 250 rpm, which is rotating speed of machine. After that, helix angle is given 17 degree and alpha is given 20 degree, that is pressure angle. So our first step is calculation of number of teeth on pinion and gear. So first of all, we will calculate the virtual number of teeth on pinion. For this, the formula is ZV1 is equal to 2F0 upon sine square alpha. The value of F0 is 1 and the value of alpha is given in the question, that is 20 degree. So after calculating, we get the value of ZV1 as 17.1. Remember that you should not round off this value, that is ZV1, to a perfect round figure. After that, we will calculate the value of Z1. This formula is present in PSG 8.1. So in this we have the value of ZV1 and beta. Putting all the respective values, we get the value of Z1, that is 14.96, which by rounding off comes out to be 15. After that, we will calculate the value of I. For this, the formula is N1 upon N2. Putting all the respective values, we get the value of I, which comes out to be 3.84. After that, we will calculate the value of Z2. For this, we use formula, that is I is equal to Z2 upon Z1. Putting all the respective values, we get the value of Z2, which comes out to be 58. After that, we will calculate the virtual number of teeth on gear. For this, the formula is ZV2 is equal to Z2 upon cos cube beta. Putting all the required values, we get the value of ZV2, that is 66.32. After that, we will recalculate the value of I. For this, the formula we are using is Z2 upon Z1. Putting all the required values, we get the value of I, which comes out to be 3.87. As you will notice that the value of I is not a perfect integer, so there is no need of adding hunting tool. So our second step is selection of material and design stresses. For this, you can refer the PSG 8.4. Based on our value of I, we will select the material. For pinion, that is 40 Ni to Cr1MO28, and for gear, we are selecting the material 15 Ni to Cr1MO15. So for the respective values, for the respective material, we will get the bending strength and contact stresses respectively. Step 3 is deciding of weaker element. For this, you can refer the PSG 8.50. So by Lewis form factor, we need to calculate the value of capital YV1. For this, the formula is pi small yv1. So the formula of small yv1 is 0.154 minus 0.912 upon zv1. So putting all the required values for the capital YV1, we get the value of capital YV1, which comes out to be 0.316. Similarly, we can calculate the value of capital YV2, which comes out to be 0.441. Now, we are calculating the strength factor for pinion. For this, the formula is Fs1 is equal to sigma b1 capital YB1. Putting all the required values, we get the value of Fs1, which comes out to be 1264 kg per centimeter square. Similarly, we can calculate the value of Fs2, which comes out to be 1411.2 kg per centimeter square. As you notice that value of Fs2 is greater than Fs1, so pinion is a weaker element, so our design will be based on the pinion. So moving further, our fourth step is calculation of module based on the beam strength. For this, you can refer the PSG 8.13a. Over there you can find this formula. In this, we will calculate the value of MT. For this, we need the design power. For this, the formula is P into SF, that is service factor. Putting all the values, required values, you get the value of design power. After that, we calculate the nominal torsional moment. For this, the formula is MT is equal to 97420 into kW upon N. This kW is the design power. Putting all the values, required values, we get the value of nominal torsional strength, which comes out to be 3653.25 kgf centimeter. After that, we will calculate the design torsional moment. For this, the formula is MT into KDK. The value of KDK taken over here is 1.3 for the symmetrical system. Putting all the required values, we get the value of design torsional moment. After that, we will put all the required values in the formula of Mn. The value of psi m we have taken as 15. So putting all the required values in the equation, we get the value of Mn, which comes out to be 0.2811 centimeter. We are increasing the module by 20% to compensate for the radial load. So after that, we get the value of Mn, which comes out to be 3.375 mm. So from PSG 8.2, we are selecting the standard module, which comes out to be 4 mm. After that, we are calculating the transverse module. For this, the formula is cos beta is equal to Mn upon Mt. Putting all the required values, we get the value of Mt, which comes out to be 0.418 centimeter. After that, we will calculate the face width. For this, our formula is psi m is equal to b by mn. Putting all the required values, we get the value of b, which comes out to be 6 centimeter. After that, we will calculate the pitch circle diameter. For this, our formula is mt into z1. Putting all the required values, the value of d1, that is pitch circle diameter, comes out to be 6.27 centimeter. After that, we will calculate the center to center distance. For this, our formula is mt, that is transverse module into bracket open z1 plus z2 bracket close upon 2. The value, putting all the required values, the value of A comes out to be 15.257 centimeter. Moving further, our fifth step is checking for the Buckingham's dynamic load. So for this, we need to calculate the beam strength of the pinion. For this, you can refer the PSG 8.51 for this formula. The formula for the beam strength of pinion is Fs is equal to sigma b 1 into b, that is face width, into mn, that is normal module, into capital YV1. Putting all the required values, we get the value of Fs is 3033.6 kgf. After that, we will calculate the tangential load. For this, the formula is mt is equal to 2 into mt upon d1. Putting all the required values, we get the value of ft, which comes out to be 1514.91 kgf. After that, we will calculate the value of ft. For this, the formula is ft plus bracket open 0.164 into Vm bracket open Cb cos square beta plus ft bracket close cos beta upon 0.164 Vm plus 1.485 under root of Cb cos square beta plus ft bracket close. You can get this formula on PSG 8.51. So in this, we need to calculate the value of Vm, that is mean velocity. For this, the formula is pi d1 into n1. Putting all the required values, we get the value of Vm, that is 189.1 meter per minute. After that, we will calculate the value of C. For this, you can refer the PSG 8.53 and table 41. So putting all the required values, the value of C comes out to be 593 Newton per mm or 593 kgf per centimeter. Putting all the required values in this equation, you will get the value of Ft, which comes out to be 2573.82 kgf. As Fs is greater than Ft, our design is safe. So moving further, if in case Fs comes less than Ft, then our design fails. So in order to overcome this failure, we need to increase the value of Mn to the next value and recalculate the value of Mt, that is transverse module, pitch circle diameter, mean velocity, tangential load and beam strength, and check for the Buckingham's dynamic load. So moving further, our sixth step is checking for the wear load. For this, you can refer the PSG 8.51. The formula for the wear, calculating the wear load, actual wear load, is Fw is equal to d1 into q into k into b upon cos square beta, where for calculating the value of q, the formula is 2i upon I plus minus 1. In case of external meshing, we will use the plus sign, and in the case of internal meshing, we will use the negative sign. So putting all the required values, we will find the value of q. After that, we will find the value of k. For this, the formula is sigma c square into sine alpha bracket open 1 upon e1 plus 1 upon e2 bracket close upon 1.4. The value of e1 and e2 is same, that is 2.15 into 10 raised to 6 kgf per centimeter square. You will get this value from PSG 8.15. Putting all the required values, we get the value of K, which comes out to be 27.5 kgf per centimeter square. So we got all the values required to calculate the value of FW. Putting all the required values, we get the value of FW, which comes out to be 1798.69 kgf. As you will notice that value of FW is less than FD, our design fails over here. So in order to make our design safe in wear load condition, we need to increase the surface hardness. For this, we assume FW is equal to FD. So after that, we will write this formula, and in this we will calculate the value of K, so which comes out to be 2.27 into 10 raised to minus 7 sigma c square. So putting all the required values in this equation, we find the value of sigma c, which comes out to be 13166.32 kgf per centimeter square. Now you need to go to PSG 8.15 for this formula, and that is sigma c is equal to CB into HB into KCL. For the value of CB, you can refer the table number 16, and for value of KCL you can refer, and for the value of KCL refer table 17. So putting all the required values, we get the value of HB, that is 526.65 BHN, that is Brinell hardness number. So this is the required surface hardness for the gear. After that, we will go to the step number 7, that is checking for the contact stresses. For this you can refer PSG 8.13. The formula for sigma c is, for the actual contact stress, is 0.7 into 1 plus or minus, sigma c is equal to 0.7 I plus or minus 1 upon A under root of I plus or minus 1 upon I into B into E upon MT. Putting all the required values, you get the value of sigma c, that is, which comes out to be 10340.04 kgf per centimeter square, as the actual contact stresses is less than the design contact stresses, so our design is safe. So at last, our 8th step is calculation of the construction parameters. So for this you can refer the PSG 8.22. So this is the complete design procedure for the helical gear. So if you like this video, then don't forget to hit the like button, subscribe to my channel, and hit the notification bell icon for more videos like this. So thank you for watching this. May God bless you.